Hello students, and welcome to this calculus lesson. In this lesson, we're going to begin learning about interpretations and applications of the derivative and the definite integral. We're going to go over 4 videos in this series, just looking at different examples. So let's get started. So we know from derivatives that the derivative of some amount is going to be the rate at which that amount is changing. So we have position and we go take the derivative of the position, then we know that we have how the position is changing, that rate, which is velocity. So in this example, we're going to look at water being drained from a swimming pool, and we're going to say that is going to be represented by r of t. So we know that r prime of t would represent the rate at which that water is going to be changing. So the derivative of r of t is going to be r prime. And since we already know what r of t, the units for r of t is, and that's going to be a cubic feet, then we know since time is measured in hours that this is going to be cubic feet per hour. So now we want to start looking at this derivative. If we're taking the integral, from a to b of a rate, we know that we have the amount of change. And specifically, we know the net amount of change, not necessarily the total amount of change without absolute values. So we're taking the integral from a to b of r prime of t dt. Well, we know that's going to be r of b minus r of a. So what does this mean? Well, that integral, which equals r of b minus r of a, represents the amount of change in the water level from a to b, from when time equals a to when time equals b, in this case, hours. So if water is being drained out of some sort of tub, we know that as the water is decreasing over this amount of time period, that, if we're saying like, okay, we're saying this is the water level at 4 seconds and this is the water at 5 seconds, we know that the water has changed this much in 1 second. So now let's look at an example problem where we can do this with. So the table here is going to be given, and in our previous video, we were just going over a table question. And so we want to approximate the value from 0 to 30 of v of t dt using a midpoint Riemann sum. We want to say what the units of measure are and what this value represents. So let's get this midpoint sum down. All right, so I'm gonna end up with 63. So let's look at what our units are. So we have minutes here and feet per minute. Since we're going up from velocity, we're going up and we're gonna end up in position because we're taking the integral here. So since we know that this is position, we're going to only be left with feet. We know that from t equals 0 to t equals 30, we know that this particle has changed position by an amount of 63 feet. One thing that I want you to notice as I put this down is that we're saying that it changes from t equals 0 to t equals 30 minutes. So always writing the units when we have those units down, you always want to be specifying what are the units. I can't just say 63 feet and that's done, because time also has a unit of measure here. And moving on to our next and final question of the video, we want to know what is the value of the integral from 5 to 25 of a of t dt. Well, as I write this down from 5 to 25 of a of t dt, we know that that is going to be equal, since we're going up from PVA, we're going up, so we're going to end up at v. So velocity, we know that this is going to be v of 25 minus v of 5. So as I get those values down from the table, that this is going to be 1.6 minus 1.6. So this comes out to be 0 feet per minute. So what does this represent for our problem? Well, we know that this represents the net change of velocity of the particle from t equals 5 to t equals 25 minutes. And you might be looking at the data in the graph and say, like, Mr. Hernandez, look, we know that at 10 seconds that it changed, that the velocity changed. And that's why I'm saying not the total amount of change, but just the net amount from beginning to end. So we know here that, okay, that's at 1.6, this one's at 1.6. So since velocity hasn't fluctuated between 5 and 25, yes, position might have changed, but the velocity at those two values is going to be the same, so we don't have a net change. And that is going to conclude our video here. We're going to go over several more examples where we're looking at different situations, different problems where we're going to end up using calculators and derivatives and integration. We're just going to continue tying everything together. So of course, if you needed any help on this video, if you didn't get some of these answers, or if you're a little bit confused on what we're doing, please reach out to me so I can help. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.